Y'all, so this is the final video of this unit. I'm going to kind of review even and odd functions again. We talked about it a little bit during class, but this will hopefully show you why we call even functions, odd functions, and a few ways to kind of be able to see these things given a graph, a chart, or even a function in itself. So I'm going to be doing this by example. The first one is going to be even. And we're actually going to take a look at our quadratic function. So f of x equal to x squared. So you guys have had some opportunities to look at the graphing part, but I wanted to just give another way that we can actually see this. So I'm going to create a chart. To represent our inputs and outputs. So in this case, our y is equal to the output of our function. So let's take a look. If we have our function being equal to x squared, that's saying put in your function, put in this input, in this case -2. Square it or multiply it by itself, and that'll be your output, or y. So we have -2 times -2, that'll give us an output of 4. Then we have -1, well, squaring that will give us a 1. 0 squared will give us 0. Put a 1 in there, square it, we'll get a 1. Square your 2, and you get 2 times 2, or 4. So here's our chart. And let's take a look at what this chart looks like on our graph. And this is something that we've sketched a bunch of times now. You've interacted with this parabola many, many times. 1, 2, 3, 4. Okay. So at -2, our y value is 4. At -1, our y value is 1. At 0, our y value is 0. At 1, it's 1. And at over 2, we're back up to 4. So this agrees with what we've been seeing on Desmos pretty frequently, that this is the shape of our parabola. So in order to figure out if this is even or odd, we're looking at a symmetry. It's a symmetry over the y-axis. So we can say that the even function is actually symmetric around the y-axis. Or in other words, you can fold this in half, you'll get this side right laying over this side perfectly. It's a mirror image of each other. So the first way we can see this is by physically folding that graph in half. The next way is by chart. So we can imagine that the 0, 0 line is our line of reflection. If we go a step to the right, our output is going to be the same as if we went to the left. So let's check this out. When x equals 1, our y equals 1. And when our x equals -1, notice how our y also equals -1, or equals 1. So we can say, all right, well, our function evaluated at 1 is equal to 1. Our function evaluated at -1 is also equal to 1. So we can say that these two outputs equal each other. And we can even see that taking 2 steps over. So we take 1, 2. Notice that an output of 2, or an input of 2 will give us an output of 4. But an input of -2 will also give us an output of 4. So again, we can see, all right, well, 2 is equal to 4. F of -2 also equal to 4. So these two are also equal to each other. So now we want to generalize it a little bit more and say, all right, well, what happens if we choose any value, x. We go x steps in the right we're going plus x steps. It's going to be the same exact thing as going x steps to the left. So x steps to the left, going to the left is a negative value, right? It's going to be the same thing as going x steps to the right, or positive x. So if we can prove this, then we've got an even function. And let's test it out for our y equals x squared. So this is the last way we can prove it, by algebra. And that's just by showing that if I replace my x with negative x, we will get the same exact simplified rule. So we have f of x equaling x squared. So we want to show that this quadratic equation representing this parabola can also show this equality. So what we've got to do is replace our x with a negative x. Simplify this thing down, and if we see that the negative x squared simplifies down to a plus x squared, we have that these two are equal to each other, and that we can generalize this not just for 1 and negative 1, 2 and negative 2, but for any positive x and for its corresponding negative x. So we know that squaring is just multiplying it by itself. And so we know a negative number times a negative number is going to give us positive, and we're left with x squared. So notice how our negative x evaluates to the same exact value as our positive. So we have shown that f of x is equal to f of negative x. So that's the even functions. Let's move on to the odd functions. So the odd functions are what they're called anti-symmetric about the y-axis. Or in other words, if we can flip it over the y and the x and it folds over on itself, then we have an odd function. So in other words, reflects over x and y. So we have our, we'll create a graph. 1, 2, 3, 4, 5, 6. And we're actually going to need to go up a little bit more. 7, 8. 3, 4, 5, 6, 7, and 8. Down this way. And then maybe 3 on each side. So for this function, we're going to take a look at f of x equal to x cubed. So again, we're going to do our xy table. Just going to choose 5 values, -2, -1, 0, 1, and 2. So take your -2, cube it, you'll actually get -2 times -2 times -2, which is 2, 4, 8. Odd amount of negatives means that this thing is going to go negative. So -1 multiplied by itself 3 times is going to be -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is actually going to be 8. So we're looking for a very similar rule to this one right here. If we look 1 step to the right and then 1 step to the left, what do we notice about those outputs? Same with 2 steps to the right, 2 steps to the left. Finally, we want to generalize it for any steps to the right, comparing it to any steps to the left. So just graphing these guys out, we get a graph that looks like this, which again should agree with what we've been looking at on Desmos, like so. And what we want to figure out, yeah, exactly what we were talking about. So right here, notice how we can flip it upside down. So this will be my in-between step. Flipped it over the x-axis. And then if I reflect that over the y-axis, notice how I get this bottom part right here. So we're saying this is anti-symmetric. But it might even be easier to see it in terms of our chart. If we take one step over to the right, notice how we get a value of 1. Whereas if we take one step to the left, we get a value of negative 1. So our function evaluated at 1 is equal to 1. Our function evaluated at negative 1 is equal to negative 1. So what you should notice here is that all you have to do to get this negative step is just put a negative sign in front of your value. So here we know that our negative value is going to be equal to the negative of the positive. And we can see that if we plug in the 1 here. So we'll get that we have a 1. And in order to make it equal to the output of the negative 1, we just need to stick a negative sign in front of it. Okay? So we can do the same thing with our 2 steps over. So 2 steps over, we find that f of 2 is equal to 8. And we also see if we take 2 steps to the right from our origin, we have that f of negative 2 is equal to negative 8. So again, we're seeing that if we take 2 steps to the left, going negative 2 steps, we're going to get the same value but a different sign as our positive steps, or the steps to the right. So notice the steps to the right is 8. We need to stick a negative sign in front of there. So in general, if you want to find an odd function, we know that the negative value, taking x steps to the left, is going to give the same exact output as f to the right, as stepping to the right, except we have to stick a negative sign in front. So that's our algebraic expression for an odd function. So let's take a look at the algebraic proof. Then I got one more thing for you guys, and then we'll be good to go. So I'm sure that you can prove this odd one algebraically. In fact, I would encourage you to do so, but I want to do a more complicated one so you can see the general strategy here. So prove algebraically that f of x equaling to x cubed plus x is odd. So we know our f of x is equal to x cubed plus x, and what we want to show is that our negative value, if we go negative steps to the left, is going to be the same exact idea, or it's going to just show the same number but differs by the sign. So we have these two places where we need to replace x with negative x. And so we look at the negative x cubed, that's just negative x times negative x times negative x. X multiplied by itself 3 times is just x cubed, and then we have an extra negative popping out. And then we do the same thing here. Well, we don't really have much to do except know that the negative sign takes over the positive. So we see that f of negative x is equal to negative x cubed minus x. So notice how they share the same exact relationship except we have a difference of signs. So the way we can remedy this is by just pulling out a negative sign from each of our terms. So we know in order to get our negative back, we got to multiply it by -1. And then to get that sign difference, we want to add x. Good check to see that if we distribute these back in, we'll get the negative versions again. So notice how we have our original function now, except with a negative sign in front. So this is going to be negative f of x, or -1 times that f of x. So we've shown that f of x is equal to negative f, or f of negative x is equal to negative f of x. So we have proven that it's odd. Check. So the last case you're going to see, I'm not going to go too into it, but it's neither. And neither is pretty easy to see. If we do something like x squared plus 1, or maybe instead x squared plus x. So this will be our new function. We try to do our negative x, and we see that we get a negative x squared plus a negative x. And so that gives us an x squared minus x. Notice how these don't really change by sign. We can pull a negative sign out of each, and it still just doesn't look the same. The signs just slightly vary. So that's just a place where nothing works. Neither even nor odd. Nor odd. Okay. So, I mean, you can even see this in terms of a chart. X and y, we'll center it around 0. And you'll also see right here, if we put in a 0 here, well, luckily we get 0. But 1, we get 1 squared plus 1, or 2. 2 squared, 4 plus 2 is 6. Negative 1 squared is a 1, but a minus 1, so we get a 0 again. And right here, negative 2 squared is 4, but we subtract 2 off, we get a 2. So notice how if we treat this 0, 0 as our border, well, we take one step to the right. Notice how our 2 is not going to be the same output as when we went here. So f of x doesn't equal f of negative x by number or sign. Okay, so that just means neither. He tested the two case, neither worked out.